And we talked about the hydraulic circuit of the Ultimate 3000. That is a UHPLC, ultra high performance liquid chromatography. We start from the bottles. In these bottles, there are 4 different solvents. And from the mixture of the 4 different solvents, we get the element. So we have 4 channels here that get into the first module of the chromatograph. That is the pump module. Okay, so you see that from here, the tubing goes, okay, let's see here, the tubing gets into the degas system. The degas system is made by a membrane pump which sucks gases out of the solutions, but it is not able to remove bubbles. From the degas system, we have 4 inlets and 4 outlets. And the outlets goes from here, here, and here, and here to the deproportioning valve. This valve is used to make the correct mixture of the 4 solvents to get the real eluent. We have 4 inlets, but only 1 outlet that goes into the pump system. We have 2 pumps inside here, and they are reciprocating pumps to deliver a very high pressure. These 2 reciprocating pumps use check valves to make the flow only in one direction. This is the purge valve. If I open the purge valve, the eluent doesn't go to the column, but will go to the waste, here and here and here and here, down here, and again down, 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 okay, there's the end of the fluidic system is over there. Okay, so if the purge valve on the converse is closed, the flow has to go here in this tubing, here, and then here, and then here. What is that? This is a mixing chamber. Why? It is full with very small beads to enable a perfect the perfect mixing of the 4 eluents, to get a constant percentage of the 4 eluents in the of the 4 solvents in the eluent. From here we go to the Reodyne system. This is the Reodyne system. It is important to see what is behind the Reodyne system. Let's see if we can, just a moment, if we can see what is behind. Yes, behind the Reodyne system, we have many channels. Just a moment, okay. It's okay. What is the Reodyne system? Okay, the Reodyne system is a device which, no, oh, just a moment. Che è successo? Si sta scaricando. Okay. Well, the Reodyne system is a device which enables the separation between the loading of the sample with the syringe, the loading of the sample with the syringe, the separation from this step and the subsequent step, that is the real injection of the sample inside the column. Let's open it here. So, do you remember? This is the tubing that goes inside the rheodine, and this is the tubing that goes to the column. But the question is, if I try to inject something with this syringe inside a system that is at 400 bar, probably I'm not able to do that because I don't have the strength to inject this sample inside a system that is at a very, very high pressure. So I need to separate the two moments. First of all, I load the sample inside a chamber that is called the loop. Can you see here the loop? We have a fixed volume, for example, in this case, it's 20 microliters. And if I load 1 liter, one liter of sample inside that loop, only 20 microliters of this liter remain inside the loop. So I have a fixed volume. I loaded the sample inside the loop. And this is not difficult because the loop is at ambient pressure. So this operation is quite easy. Now, when I turn this rotor to the inject position like this, a number of channels inside the rheodine creates so that now the loop is in connection to the pump and the column. So the flow which comes from the pump now will pass through the loop and takes the sample plug to the column. This operation happens at a very high pressure, but we have no problem because now we are separated from the ambient pressure. So the loop in the first step in the load position is at ambient pressure, and I can load the sample inside. When I turn to the inject position, the loop is in connection with the pumps and the column, so it is at a very high pressure. Okay, the core, the heart of my system is obviously the column. Please note that there's a flow direction indicated by an arrow, and you have to use the same direction to avoid that impurities that can build up at the head of the column would be eluted the next time if you reverse the position. This column, you know the characteristics of this column. You know the characteristics. Usually it is from 5, let's say, to 25 centimeter in length. The diameter can be very variable, and the stationary phase that is inside the volume is usually a C18 stationary phase. We have small beads of silica that is functionalized with an alkyl chain, and the chain is usually 18 carbon atoms long. So it is a chain. I told you before that you can mix the element, but please remember this issue. You should never go lower than 2 to 5% of methanol or organic solvent, because these chains, the chains attached last. Never go, never use mobile phases with less than 5% or 2%, but it's tricky. Let's say 5% methanol. Okay, from the column you have an entrance. Oh, sorry. No problem. And an exit. From here you go to the third module of the chromatograph, that is the UV diode array detector. Let's close here and let's open here. From the column you come, okay, the tubing is this one, comes from the column here. No, sorry, this one. And there's an in and an out. There's an inlet and an outlet, obviously. What is inside here? Inside here, there's a real spectrophotometer, different from the, well, it's a particular spectrophotometer. I told you at the beginning of the year that is a diode array detector, because think about the chromatographic peak. The peak lasts 30 seconds, and a scan of the whole wavelength range may last up to 3 minutes. This means that in 3 minutes we could have so many peaks eluting out of the column. For this reason, the classical spectrophotometer, which scans one wavelength after the other, is not suitable as a detector here. We need to separate wavelength in space and to have as many detectors as the number of the wavelength. So we have to separate them in the space, not in time, not one after the other, but all at once, all together. So with this device, we can get a spectrochromatograph. It's a 3D chromatogram in which we have on the Z axis the UV signal. On the X axis we have time as a chromatogram. Signal against time, the same. But we have a third axis, that is the Y axis, in which we put the wavelength. So we can get as many chromatograms as the number of the wavelengths we are acquiring, we are detecting. So we have a 3D surface. I will show you later in another lesson. But please remember the concept of a 3D chromatogram, signal against time and against the wavelength. Think about cocaine. Cocaine has its own absorption band. If I detect cocaine at a wavelength where it doesn't absorb, do I get a chromatograph? No, nothing. If the cocaine, let's say, for example, 600 nanometer, I'm sure that cocaine doesn't absorb at 600 nanometer. So I get a flat chromatogram. Is it clear? Flat means that I do not detect cocaine because it does not absorb at 600 nanometers. But if I take the wavelength where cocaine absorbs, I get a chromatogram. So in the y-axis, you will have as many chromatograms as the number of the wavelength you are detecting. Let's move a step further. So from the outlet here, you can go to the waste, but in our configuration, we move